Something remarkable happened on December 25, 2021. The James Webb Telescope was launched. This event will transform science and our entire view of the world. With the help of this powerful device, an observational issue in astrophysics will be ultimately overcome. James Webb will investigate the earliest ancient universe, which will reveal a plethora of secrets. Generations of astronomers will work on JWST data reduction, attempting to provide us with fresh insights into the universe. Since its launch in December, the telescope has been undergoing adjustments in preparation for its formal mission, and it was cooling down at the same time. A telescope's cooling is critical to its mission because if it becomes too hot, undesired imperfections can show on the images it takes. We certainly don't want it to happen. Today, we'll go through some of the most recent developments and learn about what the James Webb Telescope has been up to recently and, more significantly, what will happen this summer and before the end of the year. Let's get started. The freshly released JWST photos illustrate the image clarity and sharpness of 4 of the telescope's major instruments. Scientists can see that everything has finally come together. Not everything is perfectly aligned. JWST appears to be working as expected, if not better. In fact, every tested device is performing better than expected, and it appears to provide fantastic photographs. The James Webb Space Telescope orbits a point in space, unlike a planet orbiting the Sun or the Moon around the Earth. This is a dynamical equilibrium point, and it is known as L2, after the mathematician Lagrange, who described such a dynamical system. In fact, there are 5 such equilibrium points in the Sun-Earth system, and these are spots in space where we may install telescopes to better explore the universe. L2 can be found on the line connecting the Sun and the Earth from the Earth's side. L1 is on the same line as L3, but between the Sun and the Earth, whereas L3 is on the opposite side of the Sun. L4 and L5 are more unusual points that are referred to as equilateral points because they form a triangle shape with the Sun and the Earth. Different Lagrangian points can be utilized to observe different portions of the universe due to their placement. A satellite orbiting L1, for example, is useful for observing the Sun and monitoring solar spots. Instead, one located in L2 has a better view of outer space and stars, as JWST does. L2 is approximately 1.5 million kilometers away from Earth. JWST's actual position as it circles changes between around 250,000 kilometers and 832,000 kilometers from L2, keeping it out of the shadows of both the Earth and the Moon. In comparison, Hubble orbits 550 kilometers above Earth's surface, and the Moon is almost 400,000 kilometers away. Objects close to the Sun-Earth L2 point can orbit the Sun in synchronization with the Earth, allowing the telescope to stay at a relatively constant distance. What we can tell is that the mirrors were officially oriented while JWST was orbiting L2 in May, around a couple of months ago. This is a critical stage for a telescope because we can't take photographs of the universe if the mirrors aren't aligned. If our mirrors are misaligned, our images will be terrible. The first image viewable from JWST can be seen in this photograph. It displays a random star. This star was located in the middle of nowhere and was not exceptionally brilliant. It appears to be just another photograph, but if you look closely, you will notice that countless galaxies can be spotted behind the star. Consider that this was a completely random photograph with no specific observational goal, based on a very preliminary observation. Do you have any idea how many distinct galaxies we'll discover in the coming months or years? I can't wait for James Webb to be fully operational, and I'm sure you've observed the spikes around the star. What exactly are they? What causes them to form? Is this an image flaw? These spikes are technically image defects, and they can differ depending on the geometry of the telescope's mirror. The James Webb mirror is a hexagonal mirror made up of smaller mirrors. Such spikes influence not only the main star, but all the other stars in the telescope's range of vision as well. But don't be concerned. Astronomers understand how to extract and remove these spikes. It all comes down to data reduction. Once you understand the features of your telescope, you can generally get rid of instrumental flaws. The true news concerning James Webb is that the agency revealed over a week ago that the combination of the sunscreen and the active cryocooler, which is in charge of cooling down the mid-infrared sensor, also known as MIRI, has officially succeeded. The temperature of the telescope is currently at 6 to 7 Kelvin. This is the temperature at which it operates. 6 Kelvin is an incredibly low temperature that is so close to absolute zero that it is suitable for a telescope that is not impacted by instrumental heating. In the short term, the telescope is now fully operational and ready for observations. But there was more exciting news from Gaia. Gaia is an ambitious endeavor to create a three-dimensional map of our galaxy, the Milky Way, revealing its composition, creation, and development. Gaia will deliver unparalleled positioning and radial velocity measurements with the precision required to construct a stereoscopic and kinematic census of about 1 billion stars in our galaxy and the local group. This represents around 1% of the galactic star population. Gaia circles the L2 Lagrangian point as well, as shown in this image, which depicts the orbits of the James Webb Space Telescope in white and Gaia in yellow around L2. On February 18th, Gaia spotted the visitor and captured a photograph of it on the first try. Gaia received very little reflected sunlight, so Webb appears as a tiny, dim speck of light in Gaia's two telescopes, with no features visible. Gaia is not designed to take real pictures of celestial objects, the ESA explained. It instead takes extremely accurate measurements of their positions, movements, distances, and colors. However, one of the devices on board captures an image of the sky. The finding scope of Gaia, also known as the Sky Mapper. Every 6 hours, this Sky Mapper scans a tight 360-degree strip around the entire celestial sphere. The consecutive strips are slightly inclined in relation to one another, such that every few months, the entire sky is covered, touching everything that exists and is brilliant enough to be seen by Gaia. That's impressive, but what matters more is this image. I know you're probably not an astronomer, and this picture may look insignificant to you, but it demonstrates that JWTST is operational. Every other in this image is a galaxy with millions of stars somewhere out there, and every image from every instrument has a lot of different dots on it. Believe me, all of the observations will be breathtaking. We will see the universe as we have never seen it before. However, James Webb will also assist us in uncovering secrets of our own galaxy, the Milky Way. This is due to the telescope's preference for the infrared spectrum of light. Furthermore, James Webb will present us with astounding data on exoplanets and nearby planetary systems. It's funny how we often talk about such discoveries as if they'll happen in the far future, but the future is now here. In reality, the telescope appears to be ready to use. Only modest adjustments to the mirrors will be made from now on, depending on the direction the telescope will acquire due to its own motion. James Webb will essentially begin its mission during the summer because, while the telescope is mostly complete, each instrument must be carefully calibrated, and each individual team still has a lot of work to do in order for the James Webb to perform optimally. We previously said that Webb will shift orientation while in motion, but why? Is there a compelling reason why it will change its spatial orientation? As previously said, we want our telescope and instruments to be as cool as possible. This can be accomplished by restricting the amount of solar radiation that reaches the instruments. Changing the orientation of the observatory is one technique to limit this. Webb employs a massive sun shield to filter light and heat from the sun, Earth, and Moon, and its location near the Sun-Earth L2 ensures that all three bodies are always on the same side of the spacecraft. The 5-layer sun shield is made of Captain E, a commercially available polyamide film with membranes specially coated with aluminum on both sides and a layer of doped silicon on the sun-facing side of the 2 hottest layers to reflect the sun's heat back into space. Accidental tears of the sensitive film structure during testing in 2018 were among the issues causing the project to be delayed. The sunshield was designed to fold 12 times in order to fit into the payload fairing of the Ariane 5 rocket. JWST does not have a limitless field of view at any given time due to the sunshield. The telescope can see 40% of the sky from one point and can see all of the skies in 6 months, which is the time it takes to complete half of its circle around the sun. The most crucial part, though, will begin in the summer when Webb begins 460 hours of observations. During these 460 hours, Webb will attempt to teach us about 6 major topics: galaxies and intergalactic medium, galaxies, enormous black holes, planet formation, stellar physics, and star populations. All we want is for these algorithms to notice things rapidly and share all of their data as soon as possible so that scientists may begin working on data reduction and reaching new conclusions. Alright everyone, this video has come to an end. Thank you for tuning in. What are your thoughts on this video? Do you adore the James Webb Telescope as much as we do? Let us know in the comments, subscribe, and I'll see you on the channel next time.